So Atria University is India's first STEM university and is a part of Atria Group.
By 2028, can India generate $50 billion?
So, what is a battery? Let me bring this. When you put two materials together,
we are honored to have us with some of the most brilliant minds in the field of energy storage, electric mobility, and policy development. Before we proceed, I would like to take a moment to recognize and welcome our esteemed dignitaries. Our esteemed founder, Mr. Sundar Raju, Vice Chancellor Dr. Rajendra Nayak, Atria University Director Mr. Kaushik Raju, Registrar Dr. K.V. Narayanaswamy, Academic Director of COE Batteries Mr. Ravi Kumar, Academic Dean Dr. Vijay Sinha. A warm welcome as our distinguished speakers who will be sharing their expertise with us today. Professor Maria Helena Braga, Professor Aninda Jiban Bhattacharya, IIC Bengaluru, Dr. Pravir Varpanda, IIC Bengaluru, Professor Mohammad Mustafa, IISA Pune, Mr. Pankaj Sharma, Log9 Materials, Dr. Ravi Kumar, Associate Professor, Atria University. Additionally, we are honored to host a highly esteemed panel of expertise for today's discussion on government initiative and policies on emerging technologies for electric vehicles, energy storage, and beyond. A very warm welcome to Dr. Anupama Sanjeev, our esteemed moderator for today's session, Professor Maria Helena Braga, Dr. T. Mohan, Dr. Dilip G.R., Dr. Samuel Varghese, Dr. Ammu Susaina Jacob. We are thrilled to have each one of you here, and I'm assure you that today will be a day filled with enriching discussions, groundbreaking ideas, and valuable networking opportunities. To mark the official beginning of the prestigious symposium, I now invite our dignitaries, founder Mr. Sundar Raju, Vice Chancellor, Registrar, and invite our speakers to the stage for the traditional lighting of the lamp ceremony.
मुदाकरातमोदकं सदा विमुक्तिसाधकं कलाधरावतंसकं विलासिलोकरक्षकं मुदाकरातमोदकं सदा विमुक्तिसाधकं कलाधरावतंसकं विलासिलोकरक्षकं अनायकैकनायकं विलासितेवदैत्यकं नताशुभाशुनाशकं नमामि तं विनायकं नतेतरातिभीकरं नवोदिकार्कभास्वरं नमत्सुरारिनिर्झरं नतानिकापधुर्धरं सुरेश्वरं निधीश्वरं गजेश्वरं गणेश्वरं महेश्वरं तमाश्रये परात्परं निरन्तरं मुदाकरातमोदकं सदा विमुक्तिसाधकं कलाधरावतंसकं विलासिलोकरक्षकं अनायकैकनायकं विनाशितेवदैत्यकं नताशुभाशुनाशकं नमामि तं विनायकम्.
Thank you, esteemed dignitaries, for gracing this occasion and setting the stage for an insightful day ahead. To introduce Atria University and its pioneering work in the Center of Excellence for Battery Research, I invite Dr. N. Ravi Kumar to deliver the introductory speech. Please welcome.
Hi, good morning, everybody. Sorry for a slight delay because of Bangalore traffic. I blame it. and yeah, this is Ravi Kumar, Director, Center of Battery Engineering at Atria University. I don't like to waste much time. So, Atria University is India's first STEM university and is a part of Atria Group, whose flagship companies are into renewables, hospitality, and power. So, learning methodology is purely project based. The majors are mainly e-mobility, energy sciences, life sciences, and digital transformation by AML. The university has also set up Center of Excellences in the future technologies. One such is the battery engineering. So the center is fully resourced with 4 doctorates who are from different ion cell research, green hydrogen, fuel cell, supercaps, and air batteries with state-of-art equipment for research as well as academics. Myself having 2 decade experience in R&D, new product development and industrialization in primary, reserve, secondary, defense as well as commercial sector. Worked for Indian Navy. This center designs where delivers courses to the undergrads, research on the emerging technologies with organic novel material apart from conducting tailor-made training programs to industry. This year, post-graduation and PhD programs are also being started. So the problem statement for this center of battery in research methodology is to develop emerging technologies which could be disruptive to reduce one country dependence on energy storage and also the vehicles catching fire. So all the research programs are aligned with the Indian government roadmap for e-mobility rolled out by Principal Scientific Advisor in July 2024. So it's a great pleasure on behalf of Atria University to host this symposium and welcome all the guests in participating. Please be interactive with speakers by panelists to enjoy. So a brief about the speakers. I think you know everybody. Professor Maria Helena Braga is an associate prof and an integrated member of Associated Laboratory LAETA INEGI University of Porto, Portugal. She was the head of engineering physics department and also a senior research fellow at the Material Institute at the University of Texas at Austin. She collaborated and worked with the great people like Professor John Goodenough, and she has published several articles on solid state batteries. Professor Aninda Jiban Bhattacharya is a professor and JC Bose National Fellow from Research, Solid State and Structural Chemistry Unit, Indian Institute of Science, Bangalore. His research activities are mainly from physics and material chemistry. He has published several journals and patents to his credit. Dr. Prabir Barpanda is also an associate professor, Material Research Center, Indian Institute of Science. He is a material scientist and is head of Faraday Material Lab, FEMAL. He has also several credits, patents, journals to his credit. Dr. Mustafa Muhammad obtained his PhD degree from Indian Institute of Science. His areas of specialization include interfacial electrochemistry, functionalized surfaces, energy conversion, and storage devices. Water splitting, sensors, etc. He is presently a professor, Department of Chemistry, ISER, Pune, and had several articles published to his credit. And Mr. Pankaj Sharma is a technical entrepreneur and a former scientist from IIT Delhi with over 20 years of experience across building startups, fundraising, forging strategic alliances, and policy frameworking. In the past, he has worked closely with Planning Commission of India and has also been closely associated with various government bodies on developing policy frameworks around biotechnology and nanotechnology. At Log9, Pankaj is responsible for forming partnerships and alliances, government policy frameworking advocacy, strategic planning, and spearheading the people function at Log9. So now I request Atria founders, Mr. Sundar Raju, to give an inaugural speech and open up the symposium.
Lovely morning to everyone. I think we're on an inflection point, certainly as far as India is concerned, and as I've been tracking the spaces that will lead the country to the next $1 trillion in terms of GDP, I believe that this group here will be the powerhouse that drives that process. Interestingly, I think we've got Miss Helena Braga here, who I would say serendipity, if you will, is way back in, I can't remember, it was late 2018 or early 2019. I was looking for someone who would help the journey for Atria as an institute and potentially the country in terms of saying, what can we do in the renewable space to make it not so much intermittent or when resources available, but becoming a more base load potential energy. And I tried getting to University of Texas. I don't remember the sequence of events, but I got in touch with, I was connected to Ms. Braga. And I was in the US. I said, ma'am, where are you? Hoping that she'd be in Austin. He said, I'm in, Porto. And on the fly, at that moment, like I was saying, serendipity, I said, I'm going to come to Portugal on my way back. And interestingly, the journey happened. I stopped over in London, went to Oxford to figure out what we can do in perovskites, then went to Portugal, went to Porto, and I said, I'll come to the University of Porto. And landed up at the university. There were buildings after buildings, not a soul to find out. I wasn't used to using a Google map, and Google wasn't really ready then. It took me an hour and a half to find the physics department, and the only way I knew how to contact her was through a landline. I can't remember now. But amazingly, from that moment, she became my guide for Porto and Portugal. I'm trying to recollect if I went. I did go somewhere else. I think it was Lisbon. I did go elsewhere. And she became a guide and mentor in terms of how to navigate Portugal. More importantly, again, my memory fails me, ma'am. I think I got excited by the fact that you're working on, it worked with Professor Good Enough. That is good enough for me. And more importantly, and again, memory fails me, but I think you're already onto ferrites as a potential area of work. It seemed like it's an interesting new age space. So stayed engaged. Fortunately for me, while I had to disengage myself for personal reasons last few years, she stayed engaged with whoever was contacting her. And Professor Ravi Kumar was one of the people that took on the responsibility of engaging and keeping the engagement going. We're really thrilled and happy that you're here today. My hope is this is the beginning of a journey. I think we're one step away from saying energy storage will become the vehicle for renewables being the way forward in terms of energy needs. We are way short in terms of, we as a country are way short in terms of the per person units that we consume. I think if you look at internationally, the average is 15 or 17 units per person per day. I think we're in the low single digits, if you will. And there's a journey for us to travel. Fortunately, we can travel the journey on the renewable side rather than having to do fossil fuel, then exit that, and then get onto renewables. I think India, after China, will be really the leader in terms of how renewable will become commoditized. It is a commodity, commoditized as a base load energy vehicle. Today, I think, I'm hoping will be that start of an interesting journey. I like to say outcomes should be set. So I'm setting an outcome for the teams here around the renewable energy space. And I say this with a little bit of seriousness. By 2028, can India generate $50 billion annual revenue in the energy space? Feasible? I mean, it's not impossible, difficult, but feasible. So can we, through the conversations today, navigate not just what technologies are existing, because I think there's some brilliant people here who will engage us through the day, but navigate the journey to make sure that we actually aspire for an outcome. And I'm kind of starting the conversation by saying, let's set that outcome at around $50 billion by 2028 in base load renewable energy generation for the country. And I think OECD countries and certainly Europe and yourself, ma'am, are in that space of storage research, if you will. Again, a few days later, we're getting another gentleman from the NSF of USA. So I'm hoping between India, we've got from the Indian Science researchers that are outstanding, India, Europe, and America through NSF. Can we do a loosely coupled joint program that actually says this is the goal we're setting ourselves, and let's work towards that. It would be an interesting goal to set. I think at least there's a focus and direction in everything that we want to do, kind of directs ourselves. And in the process, it may be more applied research and development than basic research. But so be it, because that's as important as, translation research is more important right now for us as a country. And that's a help that I think we can, as humanity in the world, make happen through India and make happen through this team here. Again, lovely to have you all of you here. I hope this turns out to be a very interesting day for each one of us. And equally importantly, I hope at the end of the day, we will set ourselves very specific, sharp outcomes. Otherwise, we will get lost in areas that are important, but not set a direction for ourselves. I'd like to use this moment to really, Professor Bhattacharya is here. Welcome, sir. We look forward to your insights in this. We've got Professor Prabir Varpanda. We've got Ram from IISc. We've got Mustafa from IISer. And of course, we've got the industry. I mean, today's buzzword is about startups. And interestingly, when we launched this university, I think it was 2020 or so, Lognize was one of those people that came and engaged with us to say what we should do in the renewable energy space if we want to move forward. We have them here. I think together this makes an interesting thing. All of you here, I really look forward to a wonderful day of engaging conversations and a defined outcome as a process forward. Thank you very much.
Thank you so much for your wonderful inaugural speech, sir. Kicking off our technical session, we have an esteemed researcher whose groundbreaking work in social state battery technologies in reshaping the future of energy storage. Please welcome Professor Maria Helena Braga from the University of Porto.
Thank you so much for inviting me to be here. I really wanted to honor India since I read, when I was little, I read Rabindranath Tagore, and I really wanted to know India at that time. since I met Raju, um, I want to honor India much more, and I hope that we will start a new journey. And of course, not talking about the physicists that were also so important in the world, like Raman and so on. So, but also the writers. So, I'm going to start by talking about solid state and well, the batteries. So, oh, thank you. Is this working? No? This is just, it's the other way around. Okay, like this. Okay, so I'm going to do this. Okay. So I start by introducing my lab. Thanks to Professor Goodenoug's endowment, we were able to build a lab. This lab is new. It's from 2020, and it had the pandemics in the middle. But we got several boxes that you all know if you work in batteries, what they are and how they work and what are the equipment we must have inside of it to really make it good science. So these are my students. I want to also honor them because without them we would not go far. And these are several of our projects. We are funded by the European Union in a European project which is post-Lion, and also we are funded by the Portuguese government, which is also funded by the European Union anyways. So what do we want to do? We actually want, like Raju said, we want to change the world and make it more sustainable if we can. So we need for that to store energy. Why do we need to store energy? Because, as Raju said, the energy is intermittent, and we need for example, in photovoltaics, the solar cells we harness energy intermittently. So we need to, for example, during the night to have energy stored to use it during the night. If we don't have, of course, the wind farms, but even if we have the wind farms, we need to store energy. So how can we do this? We would like to do it sustainably with sustainable methods, so that we don't create a problem when we actually come up with a solution. And this, we were talking about iridium in this morning to substitute the platinum. And well, this is also as expensive, iridium. So that's what I mean when not creating a problem when we are trying to come up with a solution. So, so we want to have solutions that are environmentally friendly, inexpensive and widely available for everyone. Like, for example, sodium-based batteries. And if we can, at the same time, we would like to harvest wasted energy. There is so much pollution, right? There is so much heat that is generated that we cannot use. If we could use part of the heat that we generate in the, for example, while we store, that would be amazing, right? So, for example, the heat that is generated in data banks or in industrial, like the trash regeneration creates a lot of waste. So if we could use some part of that waste to create new energy, that would be fantastic. And how can we do that? We can do that with special materials that can emerge, that use special properties, like, for example, ferro-electrics, as we are going to see. And they are using these part of this energy to also store. So a lot of batteries have come out since I would say 2016 and so on, when people really started to work, a lot of people on batteries. And there is this hype graph that we made for this Albats project that we had in the European Union. And this is a very interesting graph. Why? Because there are several possibilities, several studies being done, for example, in zinc air, magnesium ion, structural batteries, aluminum air, and so on. But only some of them will become really commercial, like lithium ion is. Some of them will come up in a depression. People will not be able to work and to transform them into a real product. So we want to bring some solutions at least to the commercial part. And sodium ion, even if it is in the height of this curve, so the high expectancy, we think that eventually will come to be in the plateau of productivity like lithium ion. And of course, solid state. Solid state is already being made for automotives, and we have seen every day we find new advertisements and new documents and new works on several batteries. You will see something like this that we are doing for structural batteries, where you have the positive electrode in the middle and the negative all around. But wouldn't it be fantastic if we also could use emergent properties from the materials that are there? The nature gives these properties. We don't have to do anything. For example, in ferro-electric, the ferro-electricity is based on quantum properties. So can we extend the life expectancy? Can we increase the energy that we can store if we use these kind of properties? And of course, this was called quantum battery some time ago. Also, for example, the aluminum ion, it was the last one that I saw, where you have, for example, low capacity, but it's a type of technology that can last for 10,000 cycles, for example. So there is a lot of possibilities. Which ones are the ones that are going to really make the step to the breakthrough, and they are going to stay? Maybe there will be more than one adapted to what is the concept that they want to fill their needs. But of course, this was also one of the last advertisements that I saw from Toyota, that is launching their solid state battery very soon. I think in 2027, end of 2026, 2027. So there is a lot of work being done in many technologies, including solid state. I always start, don't get me wrong, I know that you know a lot about batteries, but I always start with a brief way of seeing from the physicists of what is a battery is, and then I talk about cathodes, electrolytes, and emerging batteries. So what is a battery? Let me bring this. When you put two materials together, when you put a conductor and an insulator, because the electrolyte that stays in the middle has to be an insulator, exchange electrons, or they should not exchange electrons. The electrons should go from the outside, from the external circuit, to feed our computers, our laptops, our cell phones, and so on, and our cars. So how is the energy, what is going on inside the battery where the electrons should not cross the electrolyte? So how do we equilibrate the chemical potential, the electrochemical potentials, the Fermi levels, if we have an insulator and a conductor? Because there is always the need to equilibrate the internal energy, the Fermi levels. And how is that done if we have an insulator that cannot receive or donate electrons without, of course, an external energy? That happens by forming a double layer capacitor. In this equation, you see that a double layer capacitor must form at the interfaces when you have an insulator. And that's where the energy actually is in a battery. So the energy is in that double layer capacitors that form at the interface. Then there are several types of batteries. There are like LFP, where you have an equilibrium plateau, and then while you are at the equilibrium, the two phases will have the same chemical potential, and so you can keep the voltage for while the plateau, while one phase is increasing and the other phase is decreasing. So we can keep the voltage. So what we want is to have this plateau to be larger and larger. So we want to have this equilibrium to last for the highest capacity we can get. But there are many other batteries, like NMC, for example, in which you don't have this plateau. You have a solid solution, and you use lithium while you are charging. The lithium goes from the cathode, actually from the positive electrode to the negative electrode, and while you are discharging, the other way around. But it's a solid solution, so you don't have a perfect plateau, you have like a slope. Why do we need to know this? Why do we really need to know these details of how a battery works? Because we want to know how to make a totally different battery, and we cannot make a different battery if we don't know how a battery really works. What moves the electrons? Another important thing between what is a solid state battery and a liquid battery is that in the liquid you have the liquid all around, so you have kind of a 3D lithium insertion all around the particles in the cathode, for example, and in the solid state you have much more of 1D movement, because the particles are not really well surrounded by the electrolyte most of the times. And also you must see that this, again, there are some quantum mechanics in the way the electrons come, and they have to overcome the double layer capacitor. So they have to tunnel to the other side and reduce the lithium, and then the lithium will come as a neutral particle to the cathode. So several things we need to think, and there is a probability of that lithium to move inside these double layer capacitor. So what did we do with this? Why do we need this? We need this, for example, to improve our solid state batteries. And in the Post-Lion project, we are working on NMC, and we are trying to reduce as much as possible, of course, the amount of cobalt. We all know that cobalt is mined in the Democratic Republic of Congo, and it generates a lot of imbalances in the world. So the cobalt needs to be reduced, but it's not that simple to reduce the amount of cobalt, because cobalt helps the structure of the NMC to keep coherence, because of all the magnetic properties of the NMC. So we need to have some NMC, and this is 5% of NMC, 90% of nickel, and 5% of manganese. So what did we do in this project? We were able to have many cycles with solid-state electrolytes. You see 200 cycles. How do we avoid also PVDF? PVDF is a very good binder, but in the European Union is being banned because it contains fluorine. So we need to substitute PVDF by, we were substituting PVDF by a binder that is SBR. Which is not the final solution, but at least it doesn't contain fluorine. And so what we did was that we started to understand how the curve, the discharge curve and the charge curve, how they would behave. NMC is a solid solution, and we could predict the curve just by looking into simulate the electrical properties of the NMC. You can see that the dark green is the NMC with the lithiated, so the final cathode, the lithiated cathode, and the not so the mild green is the non-lithiated, but they are a solid solution. So in a certain time, the non-lithiated will be the most stable solution when we are charging. And so you see that when we plot the simulations against the experimental work, we have pretty much a very good correlation. And why does it matter? Why does it matter to make simulations? Because we know that the electrons, as you saw, we calculated the charge carrier electrons, which corresponds to the capacity that we found experimentally. We know that now that the electrons are really, really important in the batteries, that they actually shape all the curve, the discharge curve. Of course, we are not taking into consideration the resistance, right? We are just so the resistance to the ion movement and in the battery. We are just looking into how the electrons will work, and it's amazing how important it is to actually come up with good solutions for our cathodes. So we were able, as I was telling, to charge at 200 cycles, and we were able to discharge at 3C for some cycles, and still charge at C rate for more than 120 cycles with solid state. How? Also because we knew that at the end of our charge and discharge, we had to go to the theoretical capacity at constant voltage. That was very important to keep the integrity of our cathode because of the cobalt. So this is important. What did we learn also about LFP? We were also looking into LFP. So we started to understand all the components that we have in the battery. How do they work? What are the electrical properties of the components? Because why is that important? Because we will know, for example, if we use lithium with this electrolyte, LPSCl, we know that there is a high chance that there will be a reaction between lithium and LPSCl. Why? Because the chemical potential of the lithium is there, 1.39, and the conducting band, the minimum energy of the conduction band, is actually lower than the potential of the lithium. So what is going to happen is that the lithium electrons will tunnel to the conduction band of the electrolyte. And that is not good, because at that time we are making an interface in our cell. So, but if we can predict this, if we can really know how our materials are going to work, where are the bands, the valency bands and the conduction bands, we can figure out solutions on what the materials to put in the middle of, for example, lithium and LPSCl. So we wanted to understand this. Also, from the calculation, the simulation, we can predict what will be the plateau, the theoretical plateau energy. And we can, with that, with all these knowledge, with all these numbers, we can see if we are very far away, if we have a huge resistance, because if we have a huge resistance, we will not see the equilibrium at 3.45, and we can actually know what is the cutoff voltage for charging and the cutoff voltage for discharging. So it's very important to understand the materials. This is the message, and to understand especially the electrical properties of the materials. So what did we come up with? What was our latest work? Using these materials that will bring something extra to the game without us having to do anything about it. So, ferroelectric material, by definition, is a material that will polarize instantaneously without, at a certain temperature or below a certain temperature, the Curie temperature, without having to apply a work. So this is a property of certain materials. And if we find electrolytes that have this property, then we can have energy stored without doing anything spontaneously. We don't need to charge the cell for that to happen, because they will polarize instantaneously. And then what is going to happen in the middle of your electrolyte? So the purple is in the electrolyte. How are the ions going to displace? They don't have to displace from one end to the other. Actually, they would never do it, because that's impossible. They don't have time to displace from one end, from the anode to the cathode, usually. But it's like a relay race, where each of the runners only run for a certain part of the race, and then they give the relay to the next runner. This is how it works in a polarized electrolyte. If you have dipoles, then the displacement of the ions will be much smaller, because you can use one end and then you shift the polarization. So this is how it works, and then you gain energy there. And if you have a very lithium-rich electrolyte or sodium-rich, then this is much easier, because you have sodium or lithium all around. Each of the ions only have to displace a little bit. It's like having a big hose where you already have a lot of water, or in this case, a lot of ions. So when you turn on the tap, the first water that comes out is the one that is already in the tap, in the hose. So you really don't have to displace much the ions for having the supply of ions on the electrode side. So what architectures could we do with these ferro-electric electrolytes? By the way, the equation of the composition of these electrolytes is they are lithium, sodium, or potassium free, barium 0.05, and chlorine and oxygen. So when I talk about lithium glass or sodium glass, I'm talking about these kind of compositions. So what kind of architectures could we do? We've made a lot of architectures. This is more of the traditional architecture. But on this side, instead of putting just the aluminum, we put in the copper. Why did we put copper on that side? This was just to study. We were not yet trying to be sustainable in that this will make the battery more expensive, but what we wanted to do is to bring the chemical potential down so that we had a bigger imbalance between the positive electrode and the negative electrode and the positive electrode, because this is what the voltage of your cell is all about. So we want the copper has the chemical potential down at 0.5 if you are in the She scale. But if you are in the absolute scale, it's the work function of copper is more or less 5. So you bring the chemical potential down as you want in the cathode. And here we also made some cells with lithium glass on the cathode as usual. But what is not usual is that we were able to make some cells where we put lithium on the positive electrode, so on the cathode side. How could we do this, you may ask? How can we have a lithium-lithium cell and have a voltage difference, in this case that was around 3 volts, with a plateau of 2.2, like the plateau of sulfur? How can we do this? Because the lithium actually will not play a role in the cathode, because we will align the chemical potential with the copper and with the sulfur. And the electrolyte that is in the middle, the material that is the insulator, will only see the sulfur, or will see the manganese oxide. So it will not see the lithium. If the electrolyte would see the lithium, then yes, we will have a symmetric cell. But because the electrolyte doesn't see the lithium, and the lithium can bring the chemical potential down in presence of copper and sulfur, then we have the same kind of cell that we would have if we didn't have the lithium there. And I'm going to show you in a moment the discharge of this cell. And we could also do some other cells where we put in the plasticizer, that is a dielectric material, in the middle of the electrolyte and the cathode. Why do we need that plasticizer there? It works as a on-off. So that when we discharge, the ferroelectric material keeps polarized, but the plasticizer can work can polarize and depolarize. So it will work as an on-off for the cathode material. And in the cathode material, all the lithium will stay in the cathode material. It will not cross to the electrolyte. So why do we need that? Because we want the lithium not to move too fast, because if the lithium moves too fast, we waste energy. So if the lithium will always be, if the lithium will be on the surface of the cathode material, we don't, and it will come out and in when we charge and discharge the cathode. We don't need to waste energy with the lithium moving in the cell. But we need lithium to move in the cell, and that's where the ferroelectric material enters with a lot of lithium. and the electrolyte will replenish the lithium, the lithium and the electrons in the lithium in the negative electrode. So that's where how it works. This cell works. So here it is. This charge of a cell that contains lithium, the electrolyte, and the Sn, which is the on-off, sulfur, and lithium again in copper foam. So we put it the Sn as the on-off so that we were sure that the lithium will not go anywhere from the positive electrode side. And as you see, we could actually discharge this cell for a long time. We made this actually in front of industrials that didn't believe us in the first place. But then, of course, they believed us that we could do a cell with lithium on the positive electrode. Actually, this cell contains more lithium on the positive electrode than on the negative electrode. And this lithium just works as a current collector, a normal current collector. What else can we do with a ferroelectric electrolyte? Well, there are special properties of this ferroelectric electrolyte, and this material is actually able to be a bulk insulator, but also be transport electrons through the surface. And when we can do that, we have ferroelectric topologic insulator, as it's called. And these properties are very important because some electrons can go through the surface back to the positive, to the negative electrode, to the anode, while everything in the cell happens normally, and the lithium ions displaced to the positive electrode while the cell is discharging. So what can we do with this? We can actually self-charge the cell while we are discharging. So we have a part of electrons coming through the surface, and the double layer capacitors can be working properly at the interfaces, and the lithium can, through the bulk, come to the positive, move to the positive electrode. So there we also gain some energy. So we have a material that allows us to make cells where we have self-charge properties through the surface. And why is that? Why are the electrons now go back to the anode? Because the surface chemical potentials are the other way around. So while the anode, the negative electrode has a chemical potential like this, and the positive electrode has the chemical potential like this. That's why the electrons go from the highest chemical potential to the lowest spontaneously. This is the way the battery discharges. In the surface, it's the other way around. So that's why the electrons will go from the positive electrode to the negative electrodes through the surface. So the chemical potentials of the surface are reversed to the bulk chemical potentials. So again, it's very important to understand these properties and how can we use these properties. And here is a proof of what I am showing to you and what I'm saying to you. This is actually a work from other people, from electrical engineer, and it's active photoelectrical circuits. So they use a huge circuit, electrical circuit, to simulate what we have with just one cell. This is a cell made of aluminum, or this is zinc actually. Zinc, the sodium electrolyte-based ferroelectric, and copper. And we are able to as you see, this cell is discharging, but at a certain time, the chemical potential increases. Like here in this topologic feedback circuit, exactly like this. And we made also simulations, ab initio simulations, to understand how this works. And here you see the surface with the electrons, the movement of the electrons, and the bulk keeps on being an insulator. Here it is how they made this with a huge circuit, and how we made this with just one cell. But it's exactly the same output. And this happens while the cell is being discharged with a resistor, a material resistance of 2,000 ohms, and this is a small cell of 4 by 4 centimeters. So you see how at a certain point we have an increase of potential, and then the plateau is kept for many days. In this case, I think it's just around, I don't know if this is, we have for more than 13 days plateau. And then it's going to discharge normally, and then again it's going to go up and then discharge. So this will happen for some time. So here it is, this is just this cell. Actually, this is inspired on another chemist, on Belousov Zapodinsky. Maybe you have heard about this very interesting reaction that is it is a reaction that is a feedback reaction where the reagents are the products and the products are the reagents. So instead of having a diffusion, a normal diffusion, these patterns will be created because the reagents will behave as products and the products will behave as reagents. So these beautiful patterns that I will show. Oops. How can I? You see. You see these beautiful patterns that made Belousov abandon chemistry because nobody believed in this kind of reaction. So it made Belousov abandon the chemistry, and then Zapodinsky's students took this and made all the mathematical input on this. So this is actually the same principle. If you look into the equations and the type of graphs that we obtain here, we also have a catastrophic jump up and then a discharge. It's the same kind of oscillations that we have in our cells. So we can also interpret this with Poincaré maps, but this would be too theoretical. It's just So what could we make with all this? Let me just show you a movie. So the electrolyte is sodium, lithium, and can be potassium. Here we only had, this was in the beginning, we didn't have the material for making the pouch cells now, but we made different kind of, so these are structural cells. I'm going just to show you. And now this is important. You see, we started a very dim LEDs. We heat up just one of our pouch cells, and as the cell reaches 98 degrees C, we have an increase in current while they are lighting the LEDs of 350 times. And you see how the light was really. The other thing we could do was these type of batteries that are using electrostatics. I'm going back, just let me see if I can restart. I'm just going to show you, this is be folded and so on. These were the first batteries that we could do. Of course, the common batteries. These are the common ones. These are different types. We just copper and zinc or aluminum copper. So we don't have the traditional electrodes. And here is the beam. And then after it reaches 98, we have 90 degrees. We have 350 times the current. We started with 30 microamps. We finished with 5 milliamps. Of course, we can also use them at low temperatures. And here it is, this cell, it doesn't have to touch, the electrodes don't touch. Each of the electrodes contain, one can be aluminum or zinc, the negative electrode with electrolyte, and then the other copper and electrolyte. And because of this topologic insulator way of working, we have electrons accumulated on one surface, and on the other side we have the positive charge. So we will have a cell, one electrode cell that can communicate with the other one. So we close the circuit through the air, but the cell that is formed is not, the dielectric is not the air, actually, is the dielectric, the double layer capacitor that we do in each electrode. Okay, so I'm just, maybe I don't have too much time, but I'm just going to talk about other cells that we are doing, and these are structural cells. What are structural cells? These are cells that can be put everywhere, for example, in the car roof or in the car walls. And but they have to be, of course, very inexpensive. They can use all the area that is used, and they have to withstand mechanical impacts. So they also have to have good mechanical properties. And here it is, this cell was breaking, but it was still lighting the LEDs. And it worked after. We put this cell to work after and to cycle, and it was still cycling. So here we have the cell bending. And how is this cell made of? Let me just going to show you. So this cell is made of, again, it's inspired in a coaxial cable, and it's instead of the coaxial cable where you have the insulation, which is ceramic most of the times, here we have the ferro-electric, and instead of having the same material in and out, we have a material that brings the chemical potentials to a bias, to the maximum bias we can have, but materials that are inexpensive. So we can make these cells with aluminum, as you see there, and copper, or we can make them with, for example, aluminum and just carbon. And in the middle you have the sodium electrolyte. And you can have these cells working for a lot of time at more or less 1.1 or 1.2 volts, and they can reach 1 milliamp, and these are 10 centimeters length, and the radius, the inner radius is about 2 millimeters, and the outer radius is about 6 millimeters. Okay, here again, how they work with what I was saying to you in the beginning, how they can harvest also heat, because a ferroelectric is usually a very good thermoelectric. It doesn't mean it has to be, but in this case it is. So when we heat up, we can, just by heating up, we can, while it's discharging with a resistor, we can increase the voltage. Actually, here we started by 0 and we went up to 0.9 just by heating. Here again is our the bending, all the bending tests, where we had better results with the battery than just with the shell, the outer shell of carbon, which is used in planes. And here is again another way we can use, for example, an insulator, a sustainable insulator like cork, and put, for example, these cells in the ceilings and use the extra heat, or put them in the car, and so on. So we were also working on this, and I can show to you some other movie. What did I do? And now suddenly, okay, let me see if this works. And actually, we don't have to, even with the shell, we can light the LED. Just connecting to one side, the electrostatic is so huge that even through the shell of carbon that contains a polymer, we can connect we can have the LED lit. Okay, so if you want to know more, a little bit more, you can find there. And of course, I want to thank you and thank my students and also all the projects that the funding that we had. Thank you. And of course, I'm open for discussion and for any question you might have.
Any questions, please?
I can re-explain things if you want, because maybe I was too fast. Yes, please.
So the liquid composition that you showed for MCA,
Mm-hmm.
955,
Yes,
that's a lot of nickel.
that's a lot of nickel.
You do this testing, just like you also do coin cell.
This is in coin cell.
At the industry level, that's a lot of nickel for rechargeable.
That's true.
And the second point is regarding the ferro-electric
That's,
batteries that we talked about.
let me
There's
just.
a lot of interfaces. How do you actually, if I really want to have a workable battery, that's a lot of interfaces to play with.
So in first question, you are right. This is 900505, and this is for the European project, and these are involved. We have involved battery companies, and they are the ones that actually give us the NMC to work with. This is Avesta. Do you know Avesta, the Belgium company? So they are the ones that are wanting us to work with this. So yes, I agree that this is maybe not so feasible, but because this comes from the car companies, I'm not going to say no, of course. In regards to the ferro-electric, you are totally right, but maybe I didn't explain myself too well. Let me go back to just here, okay? So the idea, if I come here, is that actually I have a lot of interfaces, and I want to have them because I gain extra energy stored on those interfaces. It's like having several capacitors, right? Of course, they are not in parallel. It would be better if they were in parallel, but in any case, I gain. But here, the idea is that the lithium will remain at the interface, will not cross, because I have the replenishment of lithium from the electrolyte. So the interfaces will be there, but it doesn't matter because I'm not needing to cross the interface with the lithium. So that's, you are right, totally right, but that's what we are doing. We don't need to have, we actually don't want to have. This cell, actually, we published this still with John Goodenough in JAX. And this cell, there was a competition between the optimization of the electrolyte. So the polarization happens in a long time, and the charge and discharge is quicker. So what we and the degradation from charge and discharge is quicker. So what we had is we had actually an increase in capacity for more than 400 cycles because we had this competition and there was not such a degradation on this cathode side. So, yeah, but you are right, it looks odd, but it's kind of more like a battery capacitor than anything else. So this is, we call them batteries, but these batteries are not, they are energy storage devices. Yeah. More questions? I'll be glad to go to any slide. Don't worry to ask. It's a good thing to ask. Yes.
Can either be created or destroyed? What's your suggestions on that statement?
You are totally right. If you are talking about the first law of thermodynamics, you are totally right. But you are a much more complex person now than you were when you had 3 years old. These kind of systems work. For example, this one, they work exactly like the equivalent circuit is like our brain, the neurons in our brain. So the entropy always wins at the end, but between two stages, in which one is the highest entropy. So between when I start and when the cell is done, I will gain more entropy. But meanwhile, there is information complexity I can create. And this is where I gain the extra energy. And this is something new since a long time ago, since Turing, for example, or since the first computer, Claude Shannon, came with information. So this is actually much more known in the computer world, where you know that you have a limit for the entropy you need to have, the Landauer limit, where you have a logarithm of 2 is the entropy limit, so you have to pay this to the devil, so you have to have errors in your computer at a certain time to pay this, right? And in your body, for example, is your temperature. You are always giving you are at a certain temperature, so you are always giving something for the entropy to go up, right? But meanwhile, you can have information, you can create knowledge, you can create complexity, you can create emergent properties, and that's what we want to have, and that's what we want to harness.
Can you change the statement energy can be created and destroyed?
No, it's not. The energy is not created and destroyed. It's just between a stage where I have a certain amount of entropy and a stage where I'm going to have more entropy, I create information. And it actually happens in an Otto cycle. In an Otto cycle, the one with the 3 times motor, you have the entropy going down in a certain, if you see the entropy versus magnetic field graph, you have the entropy going down at a certain time, so it's a cycle, and then it goes up, and then it comes down. So you use this time where it goes down momentaneously, but the entropy always wins, and there is no creation of energy, okay? You're welcome.
Go to the slide with the velocities about this, the oscillating layer.
Yes?
Now, regarding that slide with the oscillating layer, I think you try to draw a pattern between.
This one?
Yes. Try to draw a pattern between this and the battery.
Exactly.
So, My question is the kinetics similar kinetics should be similar for the situations. But one of the things in a battery is that you should know the state with a high degree of predictability, and nonlinear systems tend to be very sensitive to the initial.
Perfect question. Perfect question. Thank you for that question. You are telling me that, and you are totally right, that where you have quantum effects, where you have emergent effects, you are very close to the chaotic systems. And yes, we see, we can have these chaotic behaviors. However, we can have these chaotic behaviors within a certain range of voltages, for example, or currents. Like, for example, you know that the climate is also a complex system like this, right? But we never have the weather going to, we don't have 1,000 degrees. I hope we will not ever. So it's the same thing. The nature can keep the chaotic system in a certain boundaries. So that's what we are trying to make here, that we can do. We already know how by charging quickly, for example, for 3 minutes, we can stop the oscillations that you saw there. Because these had small oscillations as well. And you have a perfect plateau for hours. And then if you need again, then you know that you have at a certain time, kick it again. So to mitigate this behavior that you are totally right, we have. Perfect. Thank you. Did I reply to you?
Yeah.
Okay.
Last question, madam.
Yes.
How about the cost perspective of solid state batteries? As you know that the prices of LFP are coming down, and EV vehicles are becoming competitive because of this prices coming in batteries. Where does the cost of solid state batteries stand as of now?
That's a very good question as well, because of course we always, I remember, let me share with you something that I heard when I was in the Nobel Prize lunch dinner. There was someone from the committee said, well, good enough was lucky, of course he was between commas, because all the stars, he had a good solution and the market was ready for it, right? Well, it took 20 years, but still it was ready somehow after those 20 years. So sometimes the good solutions and good enough actually used to tell me that the Wilkinson, the razor was discovered many years prior, but was not introduced because the ones that made the razor blades were wanting to earn their money, and while they were commercializing the blades, they would not allow the small shaving machines. So this is the same that happens in batteries, right? So we have a lot of money invested in lithium ion, for example. There's a lot of gigafactories being sort of planned, and some of them are already failed. And so there's a lot of money invested, but it doesn't mean that solid state will not go, because it's not exactly a big change. And you see the project that we are working on is working with companies that have batteries and cars and so on. So I think that the companies, those that are going to make the change are actually the car companies, because they want a battery that can run for more time and for more kilometers, and especially it is safer, right? So the safety is here the issue. Actually, I didn't bring the first slide that I usually show, where 200 vehicles this summer in Portugal, they were burned because of one electrical vehicle in a park. This was a park for cars that were rental cars, and one exploded, and all the cars that were there parked burned immediately. So we don't want this, because this will be very bad. This is bad because of the principle, but it's also bad for the publicity and for the cars, because immediately on the news it was saying that it was a Tesla car, and then they had to shut it off because maybe there was some kind of lawsuit threatened, and then they say, oh no, it's not an electrical vehicle, then suddenly they say, and of course it was an electrical vehicle. So I think that those that are going to push, and they are the ones that are pushing, are the electric vehicles companies that are, they need very desperately a safer battery, and they are willing to pay the higher price for the batteries.
Thank you.
Welcome.
Obrigado. Now I'd like to call
Namaskara.
I'd like to call upon academic team, Mr. Vijay Sinha, to felicitate the professor.
Thank you. Thank you. Thank you. Thank you so much. Thanks.